Hello everyone. Today we are going to discuss again the third session of dual nature of matter and radiation. This is the last part of this chapter. So in this case first we are going to study regarding the Einstein's photoelectric equation. So based on Max Planck's quantum hypothesis, Albert Einstein developed a new theory in 1905 to explain the photoelectric effect. So if energy of incident radiation it is greater than the work function, then the electrons are emitted with a maximum kinetic energy. So first case we have considered that is light as a wave. So based on that they assume that the minimum frequency which is required to eject the electron, that is the threshold frequency. But Einstein here it is considered it as a particle nature. Therefore the energy of incident radiation that must be greater than the work function. Work function means the minimum amount of energy which is required to eject the electron from the metal surface. Therefore, the kinetic energy, that is maximum kinetic energy, is equal to h nu minus phi naught. That is given by h nu minus phi naught. Phi naught is the work function and h nu is the energy for that photon, or the kinetic energy that we can write it as it is half m v square maximum is equal to h nu minus phi naught, where the phi naught is the work function and v maximum is the maximum velocity and h is the Planck's constant. So the above equation is known as the Einstein's photoelectric equation. Based on this equation as well as according to this Einstein theory, what are the laws given by the Einstein that we'll see now. The first one is the photoelectric effect is possible when incident energy is greater than the work function, which is same as the laws of photoelectric effect by the wave nature. That is the minimum frequency which is required to eject the electron, that is threshold frequency. The same law here, the photoelectric effect is possible only when incident energy is greater than the work function. That is incident energy is h nu, that must be greater than the work function. Work function is phi naught, or that must be implies with h nu naught is equal to phi naught, where nu naught is the threshold frequency. It must be greater than that or it is equal to the threshold frequency. So on solving that we are getting it as half m v square maximum is equal to it is h nu minus h nu naught, or h is common, we are getting it as nu minus nu naught. The second point regarding the Einstein equation, that is kinetic energy of photoelectrons, they will depend upon the frequency of incident radiation, but it is not going to depend upon the intensity. Already in the equation first we are seeing that half m v square maximum, that is nothing but our kinetic energy. So kinetic energy it only depend upon the frequency. See here nu minus nu naught, that is nothing but the frequency here. So kinetic energy mainly depend upon the frequency of incident radiation, but here it is not going to depend upon the intensity. Similarly, the third point, the photoelectric effect is due to the absorption of photon by a single electron, that is photoelectric current, which is directly proportional to the intensity. Already in last class we have discussed regarding the laws of photoelectric effect with the graphs. So based on that, the photoelectric current that will be directly depend upon the intensity, the same theory that will be given by Einstein also. So the photoelectric current which is directly proportional to the intensity of light, but it is not going to depend upon the frequency. Then the last point, the photoelectric emission, it is a collision between the photon and an electron. So during this collision, the energy of photon that will be transferred to the electron without any time lag. Therefore, we can say the photoelectron emission is a very instantaneous process. So there will be a collision between the photon and electron takes place. So in this collision, the photon that will transfer the energy to the electron, then the electron will get a sufficient energy and it will come out from the metal surface. And this process will be taken place in a very instantaneous process, means very short time it will taken place, Therefore, the photoelectric emission, it is a very instantaneous process. So these are the 4 laws which will be given by the Einstein. Next we can study now, if V0 is the stopping potential for photoelectrons, then the maximum kinetic energy of photoelectron, that will be given by K maximum is equal to E into V0. So V0 is the stopping potential. What already we have studied what is the stopping potential. So that is a minimum negative potential with which the photoelectric current becomes 0. So for that, V0 is the stopping potential for the electron. Then our maximum kinetic energy, therefore the maximum kinetic energy we can write it as it is E into V0, or from equation 1, that half mv square maximum, that is nothing but our kinetic energy. Therefore kinetic energy E V0 is equal to, we can write it as it is h nu minus phi naught, or we can say now V0 is equal to, take this E this side, that is h by E divided by, h divided by E into nu minus phi naught divided by E we are getting. Next we will discuss regarding what are the characteristics of photon, or we can say the particle nature of light. So whenever we considered the light as a particle and it will be behaving like a photon, so what are the characteristics of that photon we will discuss. So the first point, photons are electrically neutral and do not affected of electric as well as the magnetic field. So photons are the energy packets, they are the neutral particles, therefore there will be no effect of electric as well as the magnetic field over them. Similarly, the second one, the energy and the momentum of photon are conserved in the collision. So photon and electron, they will collide with each other, but in this collision the total energy as well as the total momentum of the photon, that will be goes on conserved. In collision, photon may be absorbed or may be created, that is photon may not be conserved. Just to understand here, the energy of momentum as well as the the energy and the momentum of photon is conserved, but photon itself is not the conserved, because during collision sometimes what happens, the photon will be absorbed with the help of with the electron, or sometimes what happens, that electron will be split up and it will be created into the 2-3 parts. So the total number of photon, it is not going to conserve, but the total energy and the momentum of the photon, that will going to be conserved, and the rest mass of the photon is 0. There will be no rest mass of the photon that will be exist, that is 0 here. Similarly, one more point, the photon energy and the momentum, that will be depend upon the frequency of the radiations. So the photon energy, whatever the energy is there, the photon energy is h nu we are writing. So it depend upon the frequency itself, not the intensity. And now we are going to study, each photon is having the energy. What is that energy? E is equal to h nu, or we can write it as it is hc by lambda. Nu is nothing but it is c by lambda. Already in first year views we have studied this relation, nu is equal to c by lambda. So now we can write the momentum also. Momentum is equal to what? Mass into velocity. Therefore we can write that momentum p is equal to mass into velocity. That mass h nu divided by c we have taken already the calculation. H nu is our photon energy, that is nothing but the mass, and c is the velocity of light. So h nu by c, therefore we are getting it as it is h by lambda. So this is a momentum where h is the Planck's constant and v is the nu is the frequency and lambda is the wavelength and c is the speed of a light. Already we know it is 3 into 10 to the power of 8 meter per second. So next we will discuss now the de Broglie hypothesis. Here it is a wave nature of light. Already we have discussed regarding the particle nature of light. So then according to the de Broglie, what is the wave nature of light, that we will discuss. So in 1924, French scientist Louis de Broglie proposed a hypothesis based on the wave nature of the particle, that is moving particle of nature that should be considered as a wave like properties under suitable conditions, and they are known as the matter waves or de Broglie waves. So according to de Broglie, all the moving particles, they will move in the form of wave itself. Therefore they will hope they will good the condition or holds good the condition for the wave nature itself, and he called them as a matter waves, or we call it as a de Broglie wave. So what is a de Broglie wavelength then? A photon of frequency nu having a wavelength lambda always travel with a speed of light c. Then the energy of photon that will be given by E is equal to h nu, we know, where h is the Planck's constant and nu is the frequency. So from the theory of relativity, of Einstein, that E is equal to m into c square, where m is the mass of a particle and c is the velocity of the light. So both are the energies, that is E is equal to h nu and E is equal to m into c square. Therefore we are equating the energies from the above equation. Therefore we are getting it as h nu divided by h nu is equal to m into c square. From this equation, what is the mass of photon now? So mass of photon that will be given by m is equal to h nu divided by c square. Then the momentum that will be given by momentum p is equal to m into v, that m into v is replaced by here c, because velocity is replaced by velocity of light, that is a c. Therefore we can write m is already we have known, it is h nu by c square into c. Therefore we are getting it as h nu by c, or that implies we can write it as it is p is equal to h by lambda. Nu by c is nothing but our lambda term. So de Broglie, he assumed that this form is general, whatever the mass as well as mass of photon and the momentum we are getting. So this form is general and which is applicable to the material particles also, not only the waves, we can also apply for the matter waves also. That will be given by now. So for that matter wave, we can write the momentum m is equal to momentum p is equal to m into v. So whenever we are consider it as for radiation, we can write it as it is m into c, because for the velocity of light we can write it as c. But for materials, whenever we are going to consider that momentum p is equal to, we will write it as it is m into v. Therefore our equation becomes lambda is equal to h by p, or we can write it as it is h divided by p is replaced by mv. Next, this equation is called as the de Broglie wavelength equation. Therefore our equation becomes E is equal to half mv square. So this implies what is mv is equal to, means mv is equal to under root it is 2me, or we can write it as it is lambda is equal to h divided by, substitute that mv value in above equation. Therefore lambda is equal to h divided by mv is there, that mv is replaced by under root 2me. Then when a charged particle of a charge q is accelerated by a potential difference v, then we can say that E is replaced by QE. That is, we are considering now the charged particle which is having a charge Q and which is accelerates with a potential of or potential difference of V. So that must be implies lambda is equal to h divided by root of 2m E is replaced by QE. Now for electron we can write the equation as lambda is equal to h divided by root of 2m, Q is replaced by E for electron into V. So this is what the de Broglie equation for the electron. And the last part of this chapter now we will discuss, that is the Davison and the Germer experiment. So in 1927, C.J. Davison and L.H. Germer experimentally independently verified that the wave nature of the electron. So based on this experiment, what they have concluded means it is the electron is behaving like a wave or not, that will be discussed with the help of this experiment. That is, they found out the wave nature of the electrons. Later in 1928, G.P. Thomson also observed that diffraction effects with a beam of electrons, and Davison and Germer experimental setup is as shown in the figure. So this is the diagram of that Davison and Germer experiment. Here HT is written. HT means it is high tension, and one filament is there. F is the filament and LT is the low tension. So based on that, the electron gain, that electron will be rejected from the filament, and it will become, and it will falls on the, or it will strikes on the nickel target or the nickel crystal, and it will be scattered with all the direction, and the movable collector that will be attached to that nickel crystal, so that with the help of that movable collector, whatever the electrons which are scattered, that will be collected, and based on this there will be production of small amount of current that will be detected in the galvanometer. So these are the certain experimental setups which are shown. The same diagram we are considered again. And what are the construction of this diagram, we'll see. It consists of a tungsten filament coated with a barium oxide, and which is heated at a low potential, that is LT, low tension. Then the electrons which are emitted from the filament, that will be accelerated through a cylinder by a high voltage potential, that is HT, that high tension whenever you will apply. So first, by applying the low tension, the filament will be heated, and after that, with the help of high tension, the electrons that will be emitted from the filament, and the further the accelerated electrons, they are made to fall on the nickel plate or the nickel target or the nickel crystal through a small hole of the cylinder. Then when an electron that will be incident on the nickel plate, then these that will be scattered in all the direction, and which will be detected in the detector or the collector, you can say. The collector is free to rotate around the nickel plate. That is a movable detector, we can say. So what are the observations here? So it was noticed that a strong peak is appeared in the intensity of the scattered angle for an acceleration voltage at a scattered angle. So this peak in a particular direction is due to the diffraction of electron. They are scattered from different layers of the atoms of the nickel crystal. And according to the Bragg's law, whenever the X-ray diffraction pattern is taken, so Bragg's law diffraction of this crystal, that will be given by, it is 2d sin phi is equal to n lambda. Since phi is the glancing angle means it is the angle between that nickel target and the scattering beam, that is collector, and d is the spacing between the interplanar layers of the atoms, and lambda is the wavelength of incident light or a wave, and n is the order of the diffraction. So with the help of Davison and Germer experiment, we can conclude that electrons are also behaving like a wave, that is wave nature of electron, that will be concluded with this experiment. So here it completes the chapter, the dual nature of matter and radiation. Thank you.